let's talk about another utility of KSP, and that's using it to predict whether or not a solution will precipitate. Last year, we talked about solubility rules. But this time, solubility rules will help guide us, but they are not hard and fast. Right? It's not like something that will always be true. Sometimes things will or will not precipitate. Sulfates have a lot of exceptions in the rules, and so I didn't even have you memorize the sulfates because there are so many that are not soluble. There's many not soluble as there are that are soluble. Silver sulfate, for one of them, it's a fairly high KSP, but still appreciable in large quantities. Silver and sulfate will together precipitate. So the question is it high enough? And so for that, we would mix the two solutions. So as long as the solution has silver in it and sulfate in it in the right amounts, there may or may not be a precipitate. As long as the product of these does not go past KSP, the solution would not undergo precipitation. All right? So we can write a KSP statement for this, and it turns out to be silver squared, because there's two of them, and sulfate, SO4 -2, and so all we need to do is figure out the concentration. And so if we took a 600 ml solution of 0.1 out of this example here, it's the second one in this example, and we mixed it with 175 mils of a 0.15 molar silver solution. That's a silver nitrate, but so monosilver. Will it produce a precipitate? Right. So we're going to mix these two solutions, and so the first thing we have to do is figure out the concentration of each of the species in solution. So it turns out that the total volume that we're going to get is 775 mils. And now we have a series of dilutions. This is leftovers from Chem 1. All right, so we have to dilute this solution and figure out what the potassium concentration is. What the sulfate concentration is. All right? So the sulfate concentration after dilution, it was 0.08 molar. And so will it precipitate? Well, will it, when it's diluted, that volume will increase, the concentration will go down, and so if you do the math right, you should get 0.61 molar, 62 molar sulfate, and a similar calculation with the silver gives us that this one is the silver concentration is equal to 0.03334 molar. All right, so this is just our Chem 1 dilution problem. Here's a solution that's 600 and 175 mils, and they're diluted. This now is all in this 175, and the question is now, will they precipitate? Very standard Chem 2 problem. Do a Chem 1 problem first, and then tack on the Chem 2 idea, which is then taking these concentrations and plugging it into this equation. So if we plug those values in, again, there's no x's or 2x's or anything to solve for in this one, because we're just solving for the concentrations. Whatever this concentration is, 0.0344 molar, and squared, 0.62, 0.062 molar, 0.062 molar for the sulfate, and you plug those values in, and you multiply them out, and then you compare them to the KSP, 0.062, and I get 7.3 times 10 to the -5th, which is greater than 1.5, and so the value I get (7.3 times 10 to the negative fifth), which is just greater than the KSP, and so there should be a precipitate in this case. So that's one another way to utilize the materials. Right? All right, so let's try a slightly different problem. Again, if you're told KSP, if you know what the KSP is, silver chloride, and we say, okay, let's take some silver chloride and dump it into a silver nitrate solution. How much of the silver will dissolve? Now, Le Chatelier's principle says that less of it should dissolve because this solution, AgCl, is in equilibrium. Oi! Is in equilibrium with silver chloride. So by having a fixed high concentration of silver, less silver chloride should dissolve, and so more of it should precipitate out. And this is exactly what happens. If you drive up the metal ion in some way, oftentimes it will prevent other metals from dissolving, or prevent more of it from dissolving. Right? But we can actually calculate this. Right? We make the assumption that the silver concentration is high, and we can therefore say it's fixed. We can say that this is a, in this particular example, in a silver nitrate solution, AgNO3 is equal to 6.5 times 10 to the minus third. Well, that is going to be the silver ion concentration. We're going to say, let's just, yes, there will be a small amount of that minus x, or sorry, plus x, all right? But again, we're going to assume that the x value is going to be small, and so therefore the amount plus x will be very minimal. And so we can pretend like the external silver, like in a buffer solution, the external silver is going to be substantially high, that the silver from the forward reaction in this case will be low. So low, in fact, that's actually going to be driving backwards. And so we can predict the maximum chlorine ion concentration. So we plug this value in and just solve for the chloride ion concentration. So in that case, the Cl minus is equal to KSP divided by this value, 6.5 times 10 to the minus third. And because we can solve for the KSP, or because the KSP is known, 1.6 times 10 to the minus 10, we can plug that in and solve for this chlorine concentration. And I get 1.6 exponent negative 10 divided by 6.5 exponent negative 3. I get the chlorine concentration will be equal to 2.5 times 10 to the minus 8. And so this is the molarity, maximum molarity of the chloride. Now if we assume that all the chlorine came from silver chloride, then we know this is also the molar solubility of the silver chloride as well. So we don't have to find or plug in actual x values or solve for x, so to speak. We can do this like other equilibrium where we know all of the concentrations of the things in solution already. So this is very much like early problems in our equilibrium practice where we knew the constant, and we knew values of other things at equilibrium. In this case, it's ions that are fixed in solution. Right? So, there you go. One perfect example of this is pH. We can take the pH, we can use the pH to talk about solubility. So like, particularly, well, it's really, really easy when it is a hydroxide or something like that. So if you take a look at magnesium, 2 hydroxides, KSP statement for this will equal magnesium plus 2 hydroxide minus squared. And we can figure out what the maximum magnesium hydroxide concentration is going to be at a particular pH. So it turns out that this value, the KSP for this is equal to 1.2 times 10 to the negative 11, basically saying not much, right? But under standard conditions, we could solve for the solubility. So the solubility is then affected by pH because in solution, the hydroxide ion concentration can vary. So this problem can look one of two ways. We could solve for the minimum pH, or we could actually start to play games with the hydroxide ion concentration. We could dump in, we could throw in sodium hydroxide and say what would be the solubility. Okay? So for this particular solution, you can solve for the hydroxide ion concentration. And if you do solve for the hydroxide ion concentration, you find that the hydroxide ion concentration in solution for just dissolving magnesium hydroxide, and prove this to yourself, this will actually be one of the homework problems, will be equal to 2.8 times 10 to the negative 4th. Which, if you, so that's the hydroxide ion concentration. So this pH then would be, this would correspond to a pH equal to 10.4. Anything lower than 10.4, this value would go down, meaning more of it would dissolve. Right? So under acidic conditions, this material will dissolve. Under basic conditions, it'll precipitate. Anything lower than this. Additionally, you can decrease its solubility even more by dumping in a bunch of hydroxide, common ion effect. Right? And so you can play lots of different games with the solubility of these. If you can control the solubility of one of the ions, you can control everything. Right? And so this is what's really great about much of this chemistry that we're seeing. Right? So that's about it for solutions. You can use them to predict values of particular ions, or you can give the value of the ion, either via pH or via fixed concentrations, and use it to solve for missing amounts, which would be related to the overall solubility. Right? Remember, if you know the solubility of one, you know how much is actually dissolved. So the molarity of magnesium would be equivalent to the molarity of dissolved magnesium hydroxide. All right, there you go.